me. Let's see if that works. Okay, so my name is Bernd Wetzel. I come from the Leibniz Institute for Composite Materials at Kaiserslautern in Germany. So I'm talking about fracture toughness of and morphology, especially of block copolymer toughened epoxies. I'm talking about nanocomposites. That's what we want to develop and to improve fracture toughness, especially of epoxy resin. So epoxy resins are used in many applications, industrial applications, coming more and more. And here, for example, carbon fiber reinforced car wheels, pressure vessels for hydrogen storage, lightweight design, of course, or here in aeronautics applications, or here energy storage, flywheels which are made from carbon fiber reinforced polymer, rotating at very high speed, more than 45,000 RPM, and thus are loaded, or you will have some fatigue or fatigue crack propagation, and the material should not fail during life. So you need tough materials for that, and we have introduced nanocomposites here. And there are different options to make use of nanocomposites, but the basic principle why nanoparticles toughen a brittle epoxy resin is shown here. Yeah? So compared to a microcomposite, you introduce much smaller particles, so at the same volume content, you have much more individual particles that can interact with a crack front, or you can have crack pinning effects, plastic deformation, crack deflection, crack pinning, and so on. And these mechanisms summarize, and thus, therefore, the toughness in this case is much higher than if you would only use nanoparticles, because you have much more of these individual particles there. And now we have added, or we have used different kinds of nanoparticles. And here are shown two of them, which are more rubber-like, so they are elastic, they are plastically deformable, and therefore they can absorb energy. And in this case, we have used core shell rubber, so that's a rubber particle with a hard shell and a soft core. The size is around 100 nanometers. They bond very well to a thermosetting matrix, and this is how the microstructure looks like. So you have well-distributed individual particles in the resin, and this is a fracture surface. They have already cavitated and plastically deformed and absorbed energy. So if you would use now block copolymers, you have a different kind of polymer, and you will have the particles actually self-assembling during the processing of the epoxy resin. So in this case, 3 block copolymers, you have a stiff block left and right, and in the center you have a flexible core, and this provides the ability for plastic deformation, and the more stiff block here provides stiffness and at the same time good bonding to the surrounding epoxy resin. Actually, the final microstructure looks similar to the core shell rubber particles, okay? But, and the toughness increase is also similar. But these self-assemble, and these are already predispersed as individual particles in the resin. How do we produce the materials? So first of course, we use different kinds of resins currently, and this is just an example. So from Sika, or here from Sicomine in France, green epoxy. We tried this because 50% is based on bio, let's say, from plant origin and vegetable origin. It's more bio-based, so it's an unrigid curing system. And here core shell rubber from Canica and block copolymers from Arkema and German company Wacker. So Arkema provided nanostrength material, that's a trade name of course, and Wacker W35, which is silicon-based, so it's different than the nanostrengths. And we produce fiber composites also, means carbon fiber material we have used, but also basalt fibers. So the production process is a simple mixing of the materials. The core shell rubber are already predispersed, so you just need to mix them. And the block block copolymers need to be molten, and then they are mixed, and you get a homous mixture. Everything is casted into molds and then thermally cured in an oven, and then the material is characterized. And the mixed systems are used for hand layup, for making laminates, or for resin transfer molding processes, and then using autoclave for curing. So how are the properties looking like? Now let's look to this map. So I have collected here other data too from literature. Also the traditional fillers. So if you use compliant fillers like the block copolymers and the kosher rubber, you will find, of course, that the modulus, the Young's modulus, in this case from tensile test, is reduced. So these are normalized values. So the modulus of the composite is normalized to the value of the neat epoxy resin. Okay, so that means 1 is here, and the toughened version is also at 1, and you have an increase basically given. So the compliant fillers move in that direction. You have a very strong toughening effect, but the stiffness, the modulus, decreases. Yeah, so if you would use stiff nanoparticles like alumina or silica, you move in that direction because modulus will increase, and also toughness, but toughness increase is not so strong as if you would the compliant modifiers. Now, the target would be, of course, to move in that direction to increase both properties, modulus and toughness. Yeah, so that can be done by adding, by producing hybrids, by using the stiff fillers together with block copolymers, for example. Then you move in that direction. Now, another important properties is thermal properties, the thermal resistance. So you don't want to lose don't want to reduce the glass transition temperature of the whole system, but the traditional liquid rubbers, they have usually a reducing effect. So glass transition moves in that direction. Fracture toughness increases, of course, but that's an advantage of the block copolymers and the kosher rubber. So because due to the stiff block, we have a slight increase, or at least we do not lose any thermal properties, and glass transition at least remains on the same level, or is even slightly increased, as you can see here, for different systems. Now, we know we can toughen the epoxy resin. What happens if we use this material now in a fiber composite, in a laminate? That's what you see here. So on the x-axis, you have the toughened resin. Yeah, so the more fillers you add to the resin, the higher the toughness. So that's what you see on this axis. The critical energy release rate, G1C, is given here for the modified matrix. And if we use this modified matrix, this data point, for example, and add it to fibers, make a laminate, you get this value. So here we have the data for the laminate. And what you see is we have also an increase of toughness in the laminate. Yeah, so that's here. Maybe the matrix can be improved by a factor of 7 in toughness. A laminate is in the factor of 3 to 4. That's quite good. But there's one effect which needs to be discussed, and you can overload actually the material. If you use too much of the block copolymer, the toughness will decrease again. That's what you see here. For example, if you add the 5% of block copolymer, you have this toughness for the matrix and this in the laminate. And adding more, 10% of BCP, you can increase the toughness of the matrix, but toughness of the laminate decreases. So what happens there? The morphology changes actually, and I will come back to that later. Now it's gone. Here we go. Okay, this data was for the nanostrength block copolymers from Arkema. Now I will show you another type from Wacker in Germany, which is silicone based actually. So it's a different chemistry behind that. But as you can see, it has a similar toughening effect. Yeah. So here G1C compared now to the core shell rubber, so that's the toughness increase is similar. And also now for the bio-based epoxy resin, compared to the standard epoxy resin, we have similar toughening actually. Now there's some interesting point to see. So we can overload the material. So looking to the bio-based system with the block copolymer, if we add more than 10%, so 14 volume percent, we get a strong decrease, and the morphology has changed here. On the other hand, there's an effect that we are able to increase the toughness, and this is due to the process itself. So we have varied the curing process slightly. So all materials are cured to a standard curing process, which means 90 degrees, 105 degrees, and then 140 degrees for several hours. But in one case, we changed that, and we just left the material at room temperature for several days, and then we cured it at higher temperature according to the standard process. And what happened was the phase separation, the self-assembling of the particles changed, and the particles became much smaller. So in this case, the standard process yielded 300 nanometer sized particles, and at lower temperature gelation, we had 120 nanometers sized particles. And the toughness increased due to this by nearly a factor of 2. So what's the reason for that? And I will come to that, back to that later. But actually I will employ this example from Arkema. So, yeah, okay, but so please keep in mind these effects. Okay, but back to the smaller particles, which are obviously more beneficial for toughening. We introduced these materials also to laminate, and we use basalt fibers in this case. So basalt fiber silicone-based block copolymers, measured the fracture energy again, and compared low content and the high content of the block copolymers. And now we compared the different curing processes, also in the laminate. And this is strange, but now here you have the neat epoxy resin together with the with the basalt fiber, so that's here the reference value, and adding the block copolymers increases the toughness. But there are two effects. So when using small amount of fillers and only the ambient curing process, so leaving the material at room temperature for several days and then curing it at higher temperature, at low content, we had a lower toughness than applying the standard curing process immediately at high temperature. But at high content of fillers, it was vice versa. Yeah, so the standard curing process yielded lower toughness than the process at ambient curing. What was the reason for that? So after checking the microstructure, we found the smaller particles are present in the case where you have the higher toughness. So in this case, smaller particles were produced at standard curing process, and in this case, smaller particles were produced at ambient conditions. That's surprising, but it's consistent. So we have to control the particle size, actually. And now that means morphology of the resulting composite is crucial. So we have to control that. Now let's do some fractography and to better understand what happens here and which morphology is behind these data. Morphology of the material. Now, for the core shell rubber here, so they are already predispersed, it's no problem. They will not self-assemble, and maybe they can agglomerate, but they don't do that. So you have a homogeneous distribution here of the particles, and they have a good toughening effect. And this correlates to this data point here, maybe here, yeah. But let's have a look on these two data points. This blue one and the red one with the block copolymers, and they show different structure. So the block copolymer is actually at 5%. shows such structure. So here's a particle, but it's not nanoscale, so it's micro. And it's not cavitating, so you have some fracture structure here. So maybe particles cut, but there's also some maybe smaller particles inside. If you go to higher contents, so you use 10% of the block copolymer now, the morphology changes completely. So here you have the fracture surface, 10% BCP, looks completely different, yeah? So you have domains and and if you polish the surface, it looks like that, so completely different. And the fracture surface looks like that, so this reminds of a neat epoxy resin fracture surface because it's a brittle fracture. But something is sticking here. Is it the block copolymer? Then you have here small spherical structures. If you look in more detail to the morphology, you'll find here small particles. It should be block copolymer, and this should be epoxy resin, but we are not sure. Yeah. So where's the block copolymer? And here there are small spheres, and if you look to the details, completely different than the core shell rubber. So we wanted to understand what is going on there and find especially a method to measure this or understand it. And so how to understand the morphology at high concentrations. And we employed a new technology coming from an atomic force microscope, which can do at the same time, while topography measurement, doing infrared spectroscopy. So we can do a IR mapping of the surface. And that means we find here a spectra and representative lines for the block copolymers and here for the epoxy. And then you can provide some colors, right? And you will find that there are block copolymer-rich regions and epoxy-rich regions. And then you can overlay this together with the topography and finally find, out that you will have here block copolymer-rich faces and an epoxy-rich face, yeah? And that means if you look now and compare and correlate to the fracture surfaces from the SEM, that our spheres are epoxy-rich, right? And in between you have a block copolymer binder now generated. Now obviously, this is maybe with this content not so beneficial for the fracture toughness. So this is a new method, and I'm closing here also summarizing. Of course, we have seen the materials toughen the epoxy matrix, both the BCP and CSR. Also, laminates are toughened, and you can overload the material. You can use too much tougheners, and especially the morphology development is crucial for the mechanical property. So some acknowledgements and to the team at IBW who did all the work, and thank you for your attention.